Welcome to the Deep Dive. Today we're exploring something you probably see every single day. Just a simple sight, really, but it hides one of our planet's, most amazing secrets.
Hmm.
We're talking about ice, and that question, why does ice float?
Seems so basic, right?
Exactly. But as we dig into the sources you shared, you find this fundamental quirk about water. And honestly, if it were any different, life in our lakes, our oceans, it just wouldn't exist as we know it.
It really wouldn't. It's one of those subtle things that makes a massive difference.
A critical piece of natural engineering almost.
Yeah, you could say that.
Yeah.
And to really get why it's such a big deal, we first need to talk about density.
Okay, density. Let's break that down.
It's basically just, how much mass is packed into a certain amount of space, a certain
All
volume.
right. Okay, imagine you have two boxes, same size exactly.
Okay.
One's full of feathers, the other's packed with rocks. Which one's heavier?
Oh, the rocks, definitely, no question. Because the rocks are way denser. There's just much more stuff, more mass squeezed into that same box compared to the feathers. Feathers are, well, not very dense at all.
Okay, that makes perfect sense. So, here's the kicker, the puzzle that gets you thinking. Ice is just water, right? Frozen water.
Yep, H2O in solid form.
So you'd think, naturally, the solid version would be denser than the liquid, like most things.
That's the logical assumption for almost everything else, yeah.
But ice floats. It doesn't sink. And this is where water just kind of shows its weird side.
It really is counterintuitive.
Mhm.
For nearly any other substance, when it goes from liquid to solid, those molecules, the tiny bits it's made of, they slow down and they usually huddle closer together.
Packing in tighter.
Exactly, packing tighter, which makes the solid denser than the liquid was.
Yeah.
That's the norm.
But water's the rebel here. It doesn't follow the crowd. So what's actually happening, on the molecular level when water freezes? Why doesn't it pack tight?
Well, it does something really quite specific. As water cools and starts to freeze, the molecules do slow down, sure.
Sure.
But instead of just bunching up randomly, they start arranging themselves
Ranging. How?
into this beautiful, very organized crystal structure. Think of like a honeycomb pattern. Very regular, very open.
A honeycomb. Okay.
And here's the crucial bit. In that rigid honeycomb structure, the water molecules are actually held a bit further apart from each other than they were when they were sloshing around freely as liquid water.
Whoa, hang on. Further apart. So even though they're locked in place, they're keeping some distance.
That's right. It's because of how the water molecule is shaped, and these things called hydrogen bonds, the way the molecules link up.
Hmm.
In liquid, the bonds are flexible, breaking and reforming all the time, letting molecules slide closer.
Mm-hmm.
But when it freezes, those bonds lock into that specific, stable, open lattice structure. That structure maximizes the space between the molecules.
Same amount of water, same number of molecules. But as ice, they take up more room.
Precisely. More volume for the same mass. And if you remember our density definition, mass divided by volumes, if the volume goes up but the mass stays the same.
The density goes down. Ice is less dense than liquid water.
You got it.
I saw this analogy in the sources that clicked for me. It was like thinking about pillows and blankets.
Okay.
If you just have them in a messy pile, they take up some space. But if you fluff them all up and arrange them carefully, make them all puffy, they actually take up more space.
Yeah, that's actually a pretty good way to think about it.
It's the same amount of stuffing, the same blankets, but the arrangement makes the whole thing bigger and, less dense overall.
Exactly. The fluffed up ice is less dense.
Mm-hmm.
And because it's less dense than the surrounding liquid water,
The denser water pushes it up. Archimedes' principle, right?
Mhm.
Buoyancy, it floats.
that's the mechanism.
Yeah.
Simple physics, driven by this really unique molecular behavior.
Okay, so that explains the how. But you mentioned earlier this is, incredibly important. Why? What's the big deal about floating ice?
Well, this is where it gets really critical for, well, basically all life in fresh water,
Mm-hmm.
and even affects the oceans. It's not just a neat party trick for water.
Let's do that what-if thing. What if ice acted normally? What if it got denser and sank?
Okay, imagine a lake in winter. If ice were denser than water, as soon as it formed on the cold surface, poof, it would sink straight to the bottom.
And then more ice forms, and it sinks too.
Right, layer upon layer. Pretty soon, especially in colder climates, the entire lake could freeze solid, from the bottom all the way up to the top.
Oh, wow.
Think about what lives in that lake. The fish, the turtles, the plants, all the little critters.
It could be trapped, frozen solid. There'd be no escape.
Exactly. Winter would mean total wipeout for aquatic life in huge parts of the world,
Yeah.
year after year.
That's a completely different planet we'd be living on.
It truly is. But because water has this amazing property, because ice floats, What actually happens?
So the ice stays on top.
It forms a layer on the surface, and that layer of ice acts
Yeah.
like an insulator, a protective blanket.
An icy blanket. Okay.
Yeah, it shields the water underneath from the freezing cold air above. It slows down the heat loss from the rest of the lake.
So even if it's like really freezing outside, the water below the ice stays liquid.
It stays liquid, and importantly, it stays above freezing point, typically around 4 degrees Celsius at the bottom, where water is densest, oddly enough, but still liquid.
Creating a safe zone, a refuge.
A perfect refuge. Fish can keep swimming, plants survive, the whole ecosystem can tick over through the winter, ready for spring. It's absolutely essential.
That is actually kind of amazing. Something so simple, ice floating, enables so much life.
It really is fundamental. It shapes our planet's climate, ocean currents, and countless ecosystems.
So, wow. Next time I drop an ice cube in my drink and see it bobbing there, it's not just ice. It's a little reminder of this incredible life-saving property of water, a bit of magic, and a whole lot of science.
Well said. Water really is one of the unsung superheroes of the natural world, isn't it? So vital in ways we just take for granted.
Absolutely. And maybe that's the thought to leave everyone with today. How many other things that seem totally ordinary, totally simple,
Yeah.
how many of them are hiding these like profound scientific principles, these vital functions that keep everything working? Maybe it's worth looking a bit closer at the everyday stuff around us.
Definitely worth thinking about. What other hidden superpowers are out there in plain sight?